Last time I introduced the musical isomorphism denoted by sharp. Today I want to show you how to use it to introduce the notion of inner product for covectors. So let's recall what I said last time. If omega is a covector field, that is, omega can be written as omega j epsilon j, where epsilon j is a dual coframe. Then omega sharp, which the notation I used last time was also g hat inverse of omega, is equal to omega I, ei, where the components omega I are obtained by the components omega j of the covector field by raising an index, and this is done by multiplying omega lower index j by the inverse of the matrix, and taking a sum. Now let's give definition of inner product of covectors. So suppose that omega eta are element of Tx star M, where X is a point of M. This notation I think is clear. This is the cotangent space of M at X. Then we can define the inner product of omega and eta, writing omega sharp, eta sharp, G, that is Gx omega sharp, eta sharp. What is the formula for that? So omega sharp is given by gki omega I. I am assuming that omega is given by omega I epsilon j at p, and eta sharp is given by g l j eta j. Here I am assuming that eta is eta j epsilon j at p. Then if I use this formula, I get that omega eta, this is gkl, gki omega I glj eta j. And now we use the fact that this is the inverse of this matrix. So let's use that gkl Ki, this is delta IL, and this reduces to delta Li GLJ omega I eta J, but when you multiply the Kronecker delta symbol by this metric, you get Gij omega I eta J. This result can be written in two ways. Why? Look at the formula for omega sharp and eta sharp. Sorry, I made a typo. I should write here K and L. So these are the component of omega sharp and eta sharp respectively. So look at this formula, and from this formula you deduce that you are multiplying the inverse of the matrix Jj by omega I, which is the right component of the covector omega. So this means that you are raising an index, so you get omega j eta j, but you can also raise the index for of eta j, and you can write this as omega I eta I. This formula says also the following. It says that the matrix associated, representing the inner product of covectors is the inverse of Gij. Now let's change topic and let's talk about Riemannian distance. So far we have seen what the metric is. Now we want to start answering the question, what can we do with a metric? The first answer is to compute length of curves and to compute the distances between points. So suppose that mg is a Riemannian manifold with or without boundary. Then a parameterized curve is a map is a smooth map because gamma between I and M, where I is an interval. This interval can be open, closed, bounded, unbounded, we don't care. The reason of this is that we know how to define a smooth map also in the case where omega has a boundary, gamma has boundary points. If the interval is compact, we use the terminology curve segment. So a curve segment is a curve whose domain is a compact interval. To each smooth curve gamma, I am omitting now the adjective parameterize. This is something I will assume all the time in the sequel. You can associate velocity vector denoted by gamma prime, which lives in T gamma T M for each T in I. We will suppose that curves are regular, so a regular curve is a curve with gamma prime t different from 0 for any t in I. This implies that gamma is, let's write, a regular curve. Gamma is an immersion. Why? Because the differential of gamma, which can be identified with gamma prime, is injective. The list of definitions that we need is not finished. So if AB is a closed bounded interval in R, then a partition of AB is a finite sequence A0, A1, AK of points in AB such that A is equal to A0. This is more than A1. It's more than AK, which coincides with B. A curve segment gamma defined on AB with values in M is piecewise regular if there exists a partition of AB such that gamma restricted to AI minus 1 AI is regular in particular. This means that the restriction is smooth with non-vanishing velocity vector. A curve with this property, that is a curve segment which is a piecewise regular, will be called admissible curve, and any partition such that, let's write A0, A1, AK, such that gamma restricted to the subinterval is smooth for every I, is an admissible partition for gamma. Another definition that probably you already know is definition of reparametrization. So if gamma from I to M is a smooth curve. We go reparametrization of gamma, a curve of the form gamma tilde equal gamma composite phi. This is defined between I prime and M, where I prime is an interval and phi is a map from I prime into I, which must be a diffeomorphism. Because of the fact that this map is a diffeomorphism, there are only two possibilities. Phi prime is positive or phi prime is negative. So in this case we say that gamma tilde is a forward reparametrization of gamma, and in this case we say that gamma tilde is a backward reparametrization of gamma. Now let's give the definition of reparametrization of gamma in the case where gamma is an admissible curve. The definition I gave before works for smooth curves. Let's see what happens if gamma is an admissible curve. So our reparametrization is a curve gamma tilde equal gamma composite phi, where phi goes from CD into AB, and phi is an homeomorphism with the following property. There exists a partition C0, C1, CK of the interval CD such that phi restricted to Ci minus 1 Ci is a diffeomorphism. We are finally ready to give the definition of length of an admissible curve. So suppose that gamma is an admissible curve, then the length of gamma is given by Lg gamma equals integral from A to B times square root of G at gamma T of gamma prime T gamma prime T T, or in other terms, the integral from A to B of the length of gamma prime with respect to the metric G dt. This integral is well defined because this function here is continuous and bounded everywhere except maybe the points of the partition of AB. That is the points where gamma is not smooth. So this makes sense. It is easy to prove that the length of an admissible curve satisfies the following properties. So suppose that Mg is a Riemannian manifold, and gamma from A to B is an admissible curve, then if A is more than C is more than B, you can prove that Lg gamma, this is Lg of gamma restricted to AC, plus Lg of gamma restricted to CB. This follows easily from the additivity of the integral. Two, if gamma prime is gamma tilde is a reparametrization of gamma, then the length of gamma tilde is same as length of gamma. This follows easily from change of variable. Essentially, you have to use this formula with the fact that gamma tilde is gamma composite phi, and this means that gamma tilde prime, let's say S, this is gamma prime at phi S, phi prime of S. Then if you use this formula with gamma tilde prime instead of gamma prime and S instead of T, you will find out easily that the integral from C equal phi of A to D of phi of B of this is the length of gamma tilde, coincide with this, using the fact that phi prime S ds is dt. Okay, then let's see what is the part number 3. If phi is an isometry, between M and M tilde, where M tilde, G tilde is a Riemannian manifold, then, sorry, a local isometry, we need only a local isometry, then we have that Lg of gamma is Lg tilde of phi composite gamma. This is also easy to prove. It follows from the fact that if phi is a local isometry, then you have that phi star G tilde is equal to G, that is G tilde of d phi of V, d phi of W is G of VW for VW in TPM, where P is a point in an open neighborhood of M. You have to use this formula with V equal W equal gamma prime of T. And the result will follow immediately. Okay, now let's give definition of arc length function of an admissible curve gamma defined on the closed interval AB with values in M. So this is the function S from AB into R, defined this way: S of t equal the length of gamma restricted to the subinterval at, that is the interval from A to t, of gamma prime u g du. It's possible to prove using the fundamental theorem of calculus that S is smooth where gamma is, and S prime of t is gamma prime t g. This is what we call speed of gamma at t. Gamma is let's say gamma is a unit speed curve if the length of this vector is 1 for all t such that gamma t is smooth. Or maybe let's write in another way, at which gamma is smooth. That is, if gamma is an admissible curve, this means that this is true for all t different from the point of the partition we are considering. If this is true, what happens to this formula? It reduces to this S of t equal t minus a. So if a is 0, then we have S of t equal t, and the curve is said to be parameterized by arc length. Now, before presenting definition of Riemannian distance, I will prove the following proposition. A, every regular curve has a unit speed forward reparametrization. B, every admissible curve has a unique forward reparametrization by arc length. So suppose that gamma is a regular curve, so gamma regular, then you fix t0 in I can be also unbounded, so we have to fix what is t0. Then we can define s of t equal to this integral from fundamental theorem of calculus. It follows that s prime of t, which is equal to this function evaluated at t, is positive. So this says that s of t is a strictly increasing local diffeomorphism so this means that I is sent onto another interval I prime contained in R, So we can define phi as a S inverse from I prime into I, and then we compose it with gamma this way, and it is clear that this is a forward reparametrization. Why? Because this is positive. It remains to prove that this is also a unit speed reparametrization. So we need to prove that this is equal to 1. But this is equal to phi prime S gamma prime phi of S G, and this is equal to 1 over S prime phi of S times gamma prime of phi of S, and this is equal to 1 because S prime is this, and of course it keeps being true if T is phi of S. So this is equal to 1. Now we have to prove the part B. Suppose that gamma is an admissible curve then part A and the induction implies the existence result. I mean, there exists a unit speed forward reparametrization also in this case. Now, if gamma has only one smooth segment, that is gamma is regular, then the statement follows from A choosing I equal AB and T0 equal A. Now let's suppose that the result holds true for admissible curves with K smooth segments, and suppose that gamma has the partition A0, A1, AK plus 1. This means that now we have K plus 1 smooth segments. So by inductive hypothesis, we have that there exists piecewise regular homeomorphisms phi between 0C and AK. So this follows from the fact that the results holds true for K smooth segments. And psi from 0D onto AK B. This is true because this is a case where the curve of a curve with one smooth segment, such that gamma composed with phi is an arc length reparametrization of gamma restricted to AK, and similarly gamma composed with psi is an arc length reparametrization of gamma restricted to AK B. And remember that by definition of partition, AK plus 1 is B. So essentially what we have to do now is to put these two things together. How this is done? We define a new map, phi tilde, essentially gluing together phi and psi. This is phi s if s belongs to 0C, and psi of S minus C if S belongs to C, C plus D. So this implies that now gamma composed phi in tilde is a reparameterization by arc length of gamma. Now we have to prove the uniqueness. So this proves the existence. What about the uniqueness? Suppose that you have two reparamerizations satisfying this property. The idea is to consider the map eta equal phi inverse composite psi between 0C to 0C. Of course, phi and psi are not these two maps, but they are two distinct reparameterization by arc length. And 0C is the domain of definitions of phi and psi. So we want to prove that eta S is S, that is the composition of the inverse of phi with psi is the identity map, and this means that the psi and phi coincide. Okay, so eta is a piecewise a regular increasing homeomorphism why this is true? It is clear why this is an homeomorphism because phi and psi are homeomorphism, and why it is increasing is that they are constructed as before. So you have that the derivative of phi and psi is positive, consequently also the derivative of eta will be positive. So we have that gamma hat equal gamma composite phi composite eta satisfies this chain of identities, and now we can make this computation. Gamma at prime of S I want to show first that this is equal to 1, and secondly that this is equal to eta prime s. So the reason why this is equal to 1 is immediate by construction of phi and eta. Instead, this follows from a computation. This is equal to gamma tilde prime eta s times eta prime s g. This is equal to gamma tilde prime eta s eta prime s. This is equal to 1 by construction, and this is eta prime s. So eta prime s is 1, and since eta 0 is 0, because it sends this interval onto this interval, then we have that eta s is s as wanted. Okay, I have approximately 15 minutes. Let's now talk about Riemannian distance. So suppose that mg is a Riemannian, connected Riemannian manifold with or without boundary. Let's fix 2 points P and Q. Then the Riemannian distance from P to Q, denoted by dgpq. This is the infimum of the length of all admissible curves from P to Q. You can prove that it is well defined, and it is non-negative real number for each p q in M. Precisely, we have that this proposition says that M connected, let's write Mg connected then any 2 points of M can be joined by an admissible curve. I skip the proof of this definition because it's not very interesting in my opinion. I prefer to present another proposition which is about isometry, invariance of the Riemannian distance precisely if phi between mg and m tilde g tilde is an isometry and m tilde are connected, then the distance between phi x to phi and phi y coincide with the distance between x and g. The proof of this identity, it's not difficult, and it's a consequence of the fact that this is an isometry. Precisely, you have that g tilde of d phi v d phi w, this is gvw, you have to use this formula with v equal w equal gamma prime, where gamma is an admissible curve from from x to y, and you will see immediately, almost immediately, using the formula for the length of a curve, then you take the infimum, you will get that this is equal to this. In the last 5, maybe 10 minutes. I want to prove this technical lemma that we will use later. So let's suppose that G is a metric on W in Rn or Rn plus, and let G bar be the Euclidean metric on W. Then for every compact any compact subset K of W, there exists positive constants C, capital C, such that for all x in K, and for all V in Tx Rn, C length of V with respect to G bar is smaller or equal to the length of V with respect to G, smaller or equal to C, capital C times the length of V with respect to G bar. Essentially, this lemma gives us an estimate of the length of a generic vector with respect to a metric G in terms of the length of the same vector with respect to the Euclidean metric. Okay, let's see the proof. So let's introduce this map on the tangent space to W, writing fx v equal length of v with respect to G. The reason why you have xv here is that any point in TW is a pair xv. The reason of this is that TW is this disjoint union. So in order to identify an element of TW, you need to fix also the point. So the coordinates of a point in TW are the coordinates of the point followed by the components of the vector. Now we define L containing T Rn, defined as follows, Let's write on the left. L is the subset of TRN such that X is a point OK and the length of V with respect to G bar is 1. Since TRN can be identified with Rn times Rn, the reason of this is that I told you before that the tangent space is given by this disjoint union. Now it is intuitively clear at least that tip PRN can be identified with Rn, and here you have the disjoint union where P can be any point in Rn. So each point in TRN is a pair where you have a point and a vector, and you have that P can vary in Rn, and W is a vector in this space which can be identified with this. So it is at least clear from an intuitive point of view that you have this identification. Then you can identify L with K times S1, sorry, Sn minus 1. Why Sn minus 1? Because here I'm working with vectors of length 1. So if this is R3, and this is a vector of length 1, you can identify the vector with the endpoint, which is a point of a sphere of radius 1. In this case you have S2. In Rn you will have Sn minus 1. The advantage of working with L is that this is compact, because it's the product of two compact sets. The function f is clearly positive on L. So this implies that the length of V with respect to G can be bounded this way for each x V in L. Now, for any x in K and V in Tx Rn with V different from 0, you can write V as lambda V hat, where lambda is the length of V with respect to G bar, and length of V with respect to G bar equal 1, and lambda equal, and V hat equal V over lambda. This implies that x V hat belongs to L. Why? Because x V hat belongs to L if V hat is equal to 1, which is written here. Then you have that length of V with respect to G. This is equal to lambda length of V hat G. And this is more or equal than lambda times C, where C is this constant. And this is equal to C times the length of V with respect to G bar. So we proved that the length of V with respect to G is smaller or equal than C times the length of C times the length of V with respect to G bar. This was a proof for the case where V is non-zero. It is clear that this is true also if V is 0. Instead, for proving the other inequality, that is this one, you proceed in the same way using this inequality. And this is the end of the proof. Next time we will prove another lemma, which is a consequence of this one, which says that essentially dgpq can be bounded, can be estimated this way if P and Q are in an open subset over Riemannian manifolds with or without boundary, and if Q is a point which is not enough close to P, you can prove that distance from P to Q is larger than a positive constant D. And we will use this to show that a Riemannian metric, Riemannian manifold, is a metric space if equipped with the distance function dg. This is a good point where to stop. Thank you for your attention.